Hey there everybody, hope you're doing well. Welcome to ZimCorp. This is Python Concurrency Basic Concepts, and this is part 1, which is Understanding Concurrency. This tutorial is all about the basic fundamental concepts of concurrency that you need to understand in order to go forward with understanding the other advanced concepts, right, in Python. So without further ado, let's get started. To understand concurrency in general, we would like to take a very generic example of a restaurant. So here we have a restaurant example. This is ZimCorp kitchen, the kitchen which can give you any order you like within 10 minutes, right? It takes 1 minute to take the order and 10 minutes to prepare. So we have one chef. These are the chef's tasks. The task is to basically take the order and prepare the order. And then we've got 4 minutes. The task is divided as such. We first take the order, which takes 1 minute, and then prepare the order, which takes 10 minutes, right? So now let's go over the flow of execution. This is what the task status looks like. So the first column is the customer number, which is customer 1, 2, 3, and 4. The task is the order number because the orders represent the task, right? So we've got order 1 for customer 1, order 2 for customer 2, and so on. Then we've got the time remaining to finish the order, and then we've got the customer waiting time, how long the customer had to wait, right? So let's go over the flow real quick. The first thing the chef does is take the order, which is order 1. At this time, all the customers have to wait for a minute, right? Because they've already waited for a minute. It takes 1 minute to take the order. The next is preparing the order. So now the chef just prepared order number 1. So the time remaining for order 1 is 0 minutes. The customer waiting time is 11 minutes for all, right? So the customers have waited for 11 minutes. The good thing for customer 1 though is that the order that he or she prepared is done. So the customer 1 only had to wait for 11 minutes and the customer can go, whereas the other customers are not quite happy, right? Because they waited already for 11 minutes and nothing has happened. So customer 1 leaves, and now the chef begins to take order number 2. In this case, customer 2, 3, and 4 also end up waiting for 12 minutes because it again takes 1 minute to take the order. Then the chef prepares order number 2, and order number 2 has been finished. It took 10 minutes and 10 minutes has been added to the waiting time of all 3 customers, right? So now customer 2's order is done. Customer 2 is not that happy, but anyways, customer 2 leaves. So now coming to customer 3, the chef starts to take order number 3. So order number 3, while the chef takes the order, we've got 23 minutes for both customer 3 and customer 4, adding 1 minute to the previous 22 minutes that they had, right? So now customer 3 and 4 have been waiting for 23 minutes, and as usual, the chef prepares order number 3. So customer 3's order has been finished, and customer 3 had to wait for 33 minutes. So customer 3 leaves kind of dissatisfied, and now finally the chef starts to take order number 4. At this time, customer 4 has been waiting for 34 minutes because earlier, before the order was even taken, customer 4 had already waited for 33 minutes, and now 1 more minute for the order. So customer 4 is furious at this time, and chef prepares the order number 4. So customer 4's order is done, and it took 44 minutes to get the order done. So customer 4 leaves, but overall this is a very bad experience for the user, right? I mean the customers. So this is known as sequential execution, right? So here tasks happen one after the other. The tasks need to wait for the previous task to finish in order to execute, right? And as you saw, the process is very slow and the process is blocking. Okay, so next let's look at a different example. This basically SimCorp hired 3 more chefs, so now there are 4 chefs and there are 4 customers, right? The same thing that we had earlier. Customer 1, order 1, 10 minutes and 0 minute waiting time. So let's see how the flow goes. So each chef takes the corresponding order. Chef 1 takes order for customer 1, chef 2 for customer 2, and so on. All the customers have been waiting for 1 minute. The chefs prepare the respective orders. So all the orders are done, 0 minutes. And customer waited for 11 minutes, right? All the customers waited for 11 minutes. So once that's done, the customers are happy, they leave, and this is ideally the best scenario that we have, right? There was 1 chef per customer. So this scenario is known as parallel execution, right? Where there was a dedicated staff for each customer. So tasks happened at the same time, all the orders were prepared at the same time, right? Tasks do not need to wait for the previous task to finish in order to execute. The process is fast, it's non-blocking because none of the tasks had to wait. The orders did not have to wait, right? The orders just kept happening at the same time. Dedicated chefs for each customer was required. So this is parallel execution, right? So next, let's look at a different scenario where there are 4 chefs but 5 customers, right? So we've removed the customer waiting time from this table. Instead, we're going to add that over as the green boxes that you see below each customer, right? That's the waiting time for each customer. So everything else remains the same. Customer 1, order 1, customer 2, order 2, 10 minutes of waiting time, and so on. So let's go over the flow. So take orders, right? So what happens is 4 chefs take the orders for 4 customers. At this time, as you can see, all the customers have been waiting for 1 minute each, right? And the orders haven't even started yet. So then the chefs prepare the orders. It takes 11 minutes in total. 10 minutes in total, but the customers wait for 11 minutes, right? So as you can see, order number 1, 2, 3, 4 have finished. Order number 5 still hasn't even started. So the 4 orders are done, 4 customers leave, and we have a slightly dissatisfied customer 5, right? So customer 5 then gives the order. The chefs takes the order, and by now the customer 5 has been waiting for 12 minutes. Chef prepares the order. Customer 5 has 0 minutes remaining, and now customer 5 is highly dissatisfied. Not highly dissatisfied, the customer is dissatisfied, right? And then customer 5's order is done and customer 5 leaves. This is okay in a sense that 4 customers were satisfied and 1 customer was dissatisfied, right? So order 1 to 4 took 11 minutes and order 5 took 22 minutes. It's not that bad, but we could do better. So let's look at a different way of execution. We go back to our 10 minutes of time remaining and 0 minutes of waiting time for each customer, right? So the chefs have decided that they will focus solely on preparing the dish, right? So what they do is they hire a task scheduler, right? So this task scheduler will basically tell the chefs what to work on when, right? So let's look at an example of this. So the task scheduler tells the chefs to take the first 4 orders, right? By this time, all the customers wait for 1 minute each. Then the task scheduler tells the chefs to start preparing order 1, 2, 3 and tells one of the chef to take order number 5, right? So in this time, as you can see, order number 1, 2, 3 have 9 minutes remaining because 3 chefs are working on preparing the order. It takes 1 more minute for another chef to take order number 5. So by this time, all the customers have been waiting for 2 minutes each, right? And the order number 1, 2, 3 have 9 minutes remaining. Then the task scheduler tells the chefs to prepare order number 1, 2, 3 for 2 minutes, start order 4 for 2 minutes. Okay, so now what happens is 7 minutes are remaining because earlier there were like 9 minutes remaining, right? So now 7 minutes are remaining. Chef 1, 2, 3 work on order number 1, 2, 3 for 2 minutes each, so 7 minutes are remaining, and start order 4. So if you see earlier, order 4 had 10 minutes remaining, and so once order 4 has started for 2 minutes, we've got 10 minus 2, which is 8 minutes remaining, right? And by this time, each of the customers have been waiting for 4 minutes each, right? Next, the task scheduler tells one of the first chef to pause order number 1, resume working on other orders. So basically, chef number 2, chef number 3 and chef number 4 keep working on the orders, and chef number 1 is told to work on order 5 for 2 minutes. Okay, so what happened was, order 1 had earlier been running for, let's say, 7 minutes. Since we've paused order 1, the time is still 7 minutes remaining. Others are still running. Customer order 2, 3 and 4 are still running, so 2 minutes subtracted from each of them. So earlier order 2 had 7 minutes remaining, now it's 5 minutes remaining. Order 3 also had 7 minutes remaining, now it's 5 minutes remaining. And order 4 had 8 minutes remaining, and now it's 6 minutes remaining. Order 5, however, had not even started, and there were 10 minutes remaining for order 5. And now, since the task scheduler told chef 1 to work on order 5 for 2 minutes, we have 8 minutes remaining. And by this time, each of the customers have been waiting for 6 minutes, right? Next, the scheduler tells chef 2 to pause order number 2. The others can keep happening, as in like order number 1, 3 and 4 can keep running, and the scheduler orders the chef to work on order 5 for 2 minutes. So pausing order number 2, work on order number 5, right? So earlier, as you know, order number 1 had 7 minutes remaining, now it has 5 minutes since 2 minutes have been subtracted. Order number 2 had 7 minutes remaining as well, now it's 5 minutes. Order number 3 had 5 minutes remaining, now it's 3 minutes, right? Order number 4 had 6 minutes remaining, and now it's 4. And now order 5 had 8 minutes, now it's 6 minutes, because customer 2 decided to pause order number 2, which had 5 minutes remaining. It's still 5 minutes because it has been paused, and instead order number 5 was worked on. So from 8 minutes it went to 6 minutes. And in this scenario, all the customers have been waiting for 8 minutes. Next, as you might have guessed, the scheduler tells chef number 3 to pause. Others will resume, as in 1, 2 and 4 will resume. Order 3 will pause, and order 5 will be worked on for 2 minutes by chef 3 instead of chef 2 and 1, right? So from 5 minutes, order 1 has 3 minutes remaining, order 2 has also 3 minutes remaining, order 3 has also 3 minutes remaining, order 4 has 2 minutes remaining, and order 5 has 4 minutes remaining because order 5 is being worked on by chef number 3 for 2 minutes, right? So by this time, each of the customer has been waiting for 10 minutes each, right? So next, pause order 4. So now it's chef 4's turn, right, to work on order number 5, and pause order number 4. So all the other orders will be resumed. So order 1, 2, 3 had 3 minutes each, and since they've been worked on for 2 more minutes, just 1 minute each remains for each of the order. Customer 4's order number 4 has been paused. Now it had 2 minutes remaining, it's still 2 minutes, and now we go to order number 5 which had 4 minutes remaining, and now it's 2 minutes remaining because chef 4 worked on order number 5 for 2 minutes. So at this scenario, the customers each have been waiting for 12 minutes, right? So next, the scheduler pauses order number 5 and resumes order number 1 to 4 other orders for 1 minute each, right? So since order 1, 2 and 3 had only 1 minute remaining, they're finished, they're done. And customer 4's order number 4 had 2 minutes remaining, and since chef 4 worked on it for 1 minute, it has 1 minute remaining, right? Customer order number 5 has been paused and still has 2 minutes remaining. By this time, all the customers have been waiting for 13 minutes each, right? But none of them are unhappy. So next we finish order 1, 2 and 3, which was finished already. So it means the 3 of them can go and the 2 of them can be served. So what the scheduler says is work on order number 4 and order number 5 for 1 minute each. So as you know, order number 4 had only 1 minute remaining, and now it's 0 minutes remaining, and order 5 had 2 minutes remaining, so now it is 1 minute remaining. Okay, by this time customer 4 and customer 5 have been waiting for 14 minutes. So finally, finish order 4, customer 4 can leave, and now customer 5 remains. Work on order 5 for 1 minute is what the scheduler says. Any of the chefs can work on order number 5. It takes 1 more minute to finish the order, and we have 0 minutes remaining for order number 5 as well. So it is done. Finish order 5 and customer 5 can leave as well, right? So this was actually the best scenario. This was actually the best scenario because all the orders were fulfilled. None of the customers were dissatisfied. Order 1 took 13 minutes, order 2 took 13 minutes, order 3 took 13 minutes, 4 took 14 minutes, and 5 took 15 minutes, which is not that bad compared to the earlier scenario where one of the customer had to wait for 22 minutes, right? So this right there, this is basically known as concurrent programming, right? So this is concurrent programming. Tasks happen at almost the same time. Tasks need to wait for previous tasks, do not need to wait for the previous task to finish in order to execute. The process is fast and the process is non-blocking, right? So in parallel programming, the tasks happened at the same time. In concurrent programming, the tasks happened almost at the same time, right? And what the tasks did not need to wait, the process was fast, non-blocking. Dedicated chefs were not required, right? So 5 customers were served by only 4 chefs. This is the beauty of concurrent programming, right? You don't need to have dedicated chefs. So the chefs switched between orders, the tasks basically. So this switching was done by the scheduler, right? The task scheduler. So the task scheduler basically told the chefs to switch between different tasks, which were the orders. So yeah, this is concurrent programming, and as you see, it reduced the overall waiting time of the entire program, right? In the earlier scenario, we had in parallel programming, yes, it was the best, but I mean, you don't always have a dedicated chef for every customer, right? So you need to make do with what you have. So the beauty of concurrent programming is even if there's one chef, the chef can still serve all 4 customers in a concurrent fashion, right? The waiting time will be long, of course, because there's only one chef, but still that is possible. So this is concurrent programming. Now, in the real world, our kitchen represents the operating system, okay? Our chefs are the CPU cores, right? The customers are processes or threads. The order is the task that has been issued by the process or the thread. Okay, and the scheduler is the operating system's task scheduler. So in normal sequential programming, what you had was you had a single core and you had basically 4 different processor threads with 4 different tasks, and each of them happened sequentially, which basically customer 1 waited for 11 minutes, customer 2 waited for 22, 3 for 33 and 4 for 44 minutes. No one was happy except customer 1, which was a bad scenario. In parallel programming, we had each core for each task, right? The tasks could happen parallelly on each core, so none of them had to wait. In scenario 3, where we had like 4 chefs but 5 customers, at first what we did was we completed the 4 tasks in 11 minutes, and then the 5th task started after that, and overall the process had to wait for 22 minutes, which was not ideal for process number 5, right? So 1 to 4, process number 1 to 4 were served properly, but process number 5 had a problem. In the last scenario where we looked at concurrent programming, where a task scheduler was employed, we saw that the chefs were told to switch between various tasks. The cores were asked to switch between various tasks, right, by the scheduler, and this resulted in an overall good timing. 13 minutes for order number 1 to 3, and then 14 minutes for order 4 and 15 minutes for order 5, which is not that bad compared to earlier scenario, right? So this is the real world comparison of each of the components that we had in our restaurant. Cool. So now that we're done with understanding the basic concurrency concepts, let's move into a comparison for the same, right? So let's compare sequential versus parallel versus concurrent with the help of this table. So the property is dedicated CPU core for each task. Sequential obviously did not have that. Parallel, yes, it did. And concurrent, no, it did not, because there were only 4 chefs serving 5 customers, right? So no dedicated CPU core in case of concurrent and sequential. In case of parallel, yes, 4 chefs, 4 customers. Scheduling, not required for sequential, only 1 chef. Parallel, no, because dedicated chefs per task. And concurrent, yes, it was required. What about faster execution? Sequential was very slow, as you saw, 11 minutes, 22 minutes, 33 minutes and 44 minutes for the customers, right? It was very slow. Parallel, of course, it's going to be the fastest because there's a dedicated CPU core for each process. And concurrent, even if it did not have a dedicated CPU core, it was still fast, right? So non-blocking code execution. Sequential was blocking all the way from order number 1 to 4. It was completely blocking. For parallel, nothing was blocked because a dedicated core again. And in case of concurrent, even if the number of cores were less than the number of tasks, it was still non-blocking, right? The tasks happened simultaneously. Resource utilization, sequential is pretty bad. Parallel and concurrent were pretty good. Actually, parallel is good for resource utilization. Concurrent is the best because you used 4 CPU cores to reduce the overall time for 5 different tasks, right? Now, what about race conditions and deadlock issues? So race conditions and deadlock issues are something we have not discussed yet. Race conditions are related to when 2 or more tasks share the same resource and they try to somehow update or read it. One updates it and the other reads it before the update, causing inconsistency. So we'll get to race conditions later. We'll look at it in great detail in upcoming courses. In this course as well, we will look at race condition in brief. For now, what we need to understand is there is a shared resource which needs update and read and write. Basically, there's a read operation, there's a write operation, and since parallel and concurrent, right, they both happen simultaneously, we need to make sure that the read and write are happening consistently, like one updates the value properly before other reads it, things like that. So that is basically, there are a lot of examples for race conditions. We'll go over that in another upcoming course which we will have. I'll mention that at the end of this course as well. And we also have deadlock issues. So deadlock is basically when one process is waiting for something from the other process, and the other process is also waiting for something from the real process. I mean, process 1 waits for something from process 2, process 2 waits for something from process 1, and none of the processes can move forward, right? That's a deadlock issue. So in parallel and concurrent programming, race conditions and deadlock issues will exist, right? We'll go over that later also. And what about cost? So sequential is not costly at all. Parallel is very costly because you need a dedicated core for each task. Concurrent depends, right? So it depends how many cores you have and how well you can schedule the task to serve the process and thread, right? So these were all the differences, and if you see, parallel and concurrent are not really that different, right? They're kind of the same. So let's look at what the difference is between parallel and concurrent. The only difference is having a dedicated CPU core per task, right? As you saw earlier. Concurrency does not need dedicated CPU cores and switches between tasks. This is the illusion of parallelism. So in concurrency, things are not happening at the same time always. The tasks are switching between one another, and this actually gives you the illusion that they're happening at the same time. So this is the illusion of parallelism. You can say that concurrency is the illusion of parallelism as well. Next, concurrency can execute multiple tasks with any number of cores, even if there is one core, right? In parallelism, if there's only one core, basically it's sequential programming, right? Because in parallelism, tasks do not, the processor will not switch between tasks. So the chef will only process one order at a time, right? That's the idea. And if it was concurrent, even if there is one chef, the chef could switch between different tasks, different orders, and give you the result. But yeah, so if there is a dedicated core for each task available in the CPU, for example, if you have 4 cores and you have 4 processes, then the operating system will execute things parallelly. However, if you have 4 cores only and let's say 20 processes, it's not possible for the operating system to assign each task to each core, right? So the operating system automatically switches to concurrent flow when the available cores are less than the number of tasks. So this is the only difference. These are the differences between parallelism and concurrency. The CPU cores available, right? And the other difference is obviously a task scheduler. So a task scheduler is required for concurrency, not for parallelism. Great. Now this begs the question, right? Don't we always want parallelism, right? If we can afford it, don't we always? So if we can afford it, yes. But maybe not always, even if you can afford it. Even if you can afford it, maybe parallelism is not the best idea always. Let's see why. Parallelism wastes a lot of resources. As you saw in example number 2, right? 4 chefs were only used for 4 different processes, 4 different tasks. So in the real world, most tasks are handled by different processes, okay? For example, the chef could be doing the cooking and the cashier could take the order, right? So a resource utilization could be done in this way. If this was completely parallel, strictly parallel, we would need 1 core for the cashier, 1 core for the chef. In concurrency, that's not the case, right? The CPU OS can switch between the cashier and the chef as well, right? So that's one case. So the chefs would not have to wait until the orders are taken. The cashier could take the order, right? this time could be utilized into doing something else. The chef could be doing something else other than waiting for the orders to be taken. So not only is parallelism costly, but also inefficient in terms of resource utilization. And even though it is the fastest, it could be done better if it was concurrent. You would not even need all 4 dedicated cores, right? You could maybe achieve better results with 2 cores. So concurrency is the best option. It utilizes better the resources better and gives us an overall good speed of execution, right? So we don't always need parallelism. That's why we are studying concurrent programming, right? And even though you have books like parallel programming in Python or something like that, they all focus on concurrency. Like they will always focus on concurrency because the task switching happens at the CPU level, not at the code level, right? Even if we create processes, even if we create threads, they're created at the operating system level, and the operating system level always runs a task scheduler. So in the end, it is all concurrency, not dedicated cores for task, right? So we're always picking concurrency from now on. Great. So now let's look at some terminologies for concurrency. This is going to be very important. I want you to remember the words that are highlighted in red color. Okay, so here we go. So this is the formal definition for concurrency: the process of performing multiple tasks at once by switching between them simultaneously, giving the illusion of parallelism. You already know how the illusion of parallelism is given, how the tasks are switched by the task scheduler, right? So this is the formal definition. This process of switching between tasks is known as context switching. This is a very important term. Context switching is basically the task scheduler telling the CPU to switch between different processes. That switching is known as context switching. It is considered to be an overhead. Now, what is an overhead? Overhead, you can think of it like something which has to be done, but you don't wish that it existed. You don't wish you had to do it, right? It's some sort of a problem which kind of exists and you can do nothing about it, but you wish that problem did not exist. So in this case, it would be really great if context switching did not exist. If the CPUs could just switch between tasks just like that, didn't have to waste some certain amount of time. But that's not possible, because if the CPU is switching between something, it does take at least a few milliseconds, right? Nanoseconds or even like microseconds, whatever, but it does take some time. So that is the overhead that exists. So context switching is an overhead, and it exists when CPUs are switching between tasks. Next, there are various switching mechanisms, okay? The one that we looked at with the restaurant example, where one chef was told to work on one order for 2 minutes each, right? And then switch to another order. This kind of algorithm is known as round robin, right? Where tasks get a specific time and then the OS switches to another task, okay? Now, these switching mechanisms are known as scheduling algorithms. If you look it up online in another tutorial, maybe you'll see that it's called a scheduling algorithm. There are various scheduling algorithms, a lot of them exist, and the most popular one is round robin, which we just saw an example of. It's not exactly accurate as the real world round robin, but you get the idea, right? And the core will basically switch between the core will work on a particular task for a certain amount of time, and then the OS will tell the core to switch to another task. The switching again is handled by a task scheduler. So in some cases, right, like the one we saw in the restaurant example, the tasks not the one that we saw in the earlier example, the tasks will leave the core by themselves. So we will look into this scenario later, as in there is no need for a task scheduler in this scenario, okay? In some cases that we discussed about in this point number 7, right? The tasks themselves will leave the core. So think of it like somehow the orders that you made, right? The the order somehow gains sentience, becomes conscious, and tells the chef that no, you've been working on me for too long, just go to some other order. But that does not happen, so a task scheduler was required. But in some cases, the tasks will themselves leave the core when they are not busy. Okay, we'll look into this scenario in the upcoming videos. So when the switching is handled by the task scheduler, it is called preemptive multitasking. Okay, this is known as preemptive multitasking. A task scheduler will preempt the task from running and let another task take the core, the CPU core. Right? This is known as preemptive multitasking. If you look at the definition of preempt, it means to leave, kind of like order someone to leave or something like that. So preemptive multitasking is basically when the task scheduler tells the task to leave the core. In this case, in our case, it tells the order to stop and tells the chef to work on another order. So this is preemptive multitasking. In the scenario that we talked about in point number 7, right, when we said that the tasks leave the core by themselves, this is known as cooperative multitasking, because the tasks themselves cooperatively cause concurrency to happen and no task scheduler is required, right? Since I have told you that we'll look into this scenario later, point number 9 also we'll look into later. So we'll look at cooperative multitasking later. For now, what we saw was preemptive multitasking by the help of a task scheduler. So we'll look at cooperative multitasking later. So we have seen preemptive multitasking. Great. So sequential execution, parallel execution, and concurrent execution, we understood their key points and the differences between sequential, parallel, and concurrent execution. We also looked into a few terminologies like context switching, preemptive multitasking, task scheduler, and what they are and how they work. We should look into another concept which is known as inherently sequential versus parallelizable tasks. In concurrency, not everything can be made concurrent, right? What I mean by that is there are some tasks which need to happen in sequence, one after the other. You need the result of the previous operation in order to execute further. These types of tasks versus there are some tasks which can be made parallel, as in they are independent of one another. So we'll just look into what these terms mean and we'll understand better what these terminologies stand for. Let's first look into the inherently sequential or non-parallelizable task. So these are the tasks that cannot be executed parallelly, right? These are dependent on one another, as in one task needs to finish before the other can execute, right? The execution of the next task depends on the result of the first task, right? Let's if we remember our restaurant example, we had an order and the order had two steps, which were take the order and then prepare the order. If you think about it, you cannot prepare the order without taking it, right? So this is basically an example of a sequential task. You have to take the order and then prepare the order. The preparation cannot happen without taking the order. This is a prime example of a sequential task in terms of our restaurant example. Now that we looked into the restaurant example, let's look into some real world scenarios of sequential tasks. So the first one is Fibonacci series. The Fibonacci series is basically a series of numbers where each item in the series is a sum of the previous two items, right? The first item and the second item are constants, which are both 1 and 1. The second term is a sum of the previous two. The third term is also the sum of the previous two, and it goes as and so on. So what is inherently sequential in them? Basically, term 2 needs term 1 and term 0, term 3 needs term 2 and term 1, and so on, right? They are dependent on the previous outcomes. Here we have the first term, which is 1, the second term which is also 1, these two are constants. Then we have 2 which is the sum of the previous two ones, and then the next term is 3 which is the sum of the second term and the third term, right? And this goes on forever. There's no limit to it. It can go as much as you want. This is one prime example of sequential tasks. Let's look at another one. Another one would be merge sort. So in merge sort, what we do is we have an unsorted array. We break the array until we encounter a single element, and then we join the array in order. Let's look at how that happens. We have an unordered array. So we break it down into two halves. There are still 2 elements in each half. So we further break it down, and finally we get single element arrays, right? Now we can stop. And now the joining of the array happens, and the joining has to happen in order. You can traverse these paths separately, parallelly, but in order to construct the parent array, you have to construct the child array. So that's why this is sequential in nature. And let's look at how the joining happens. The joining happens as follows. You can see 2 and 5 and 1 and 9 got sorted and joined together, and finally you get the entire sorted array. So the sequential part about this merge sort algorithm is that the smaller array needs to be built for the larger array to be built. It cannot happen without the previous one. Another example of inherently sequential task is writing to a file in order. Say I have a file and I have 4 different threads, each wanting to write a number. However, I want these numbers to be written in order, right? So how do I do that? If I do this parallelly, there is no guarantee that the numbers will be in order, because threads can execute at any given time and finish at any given time, right? The 4th thread can finish before the first, and so on. So what we need to do is, even if there are multiple threads, the threads needs to go one after the other as follows. First 1 needs to write, then 2 needs to write, then 3 needs to write, and then 4 needs to write, right? They cannot write ahead of the previous number. So that's how this task is also sequential in nature. The very last example that I want to give for inherently sequential task is querying the database, right? So you have a query, you have the database, you make the query, and only then do you receive the results. You cannot receive the results without making the query, right? These are basic examples of inherently sequential tasks in the real world. Now that we've got that clear, let's move on to the next section, which is parallelizable tasks. Now these are the exact opposite of inherently sequential tasks, as these are tasks that can be executed parallelly. These tasks are not dependent on one another. They do not need to wait for each other to finish, right? In case of our restaurant example, we have the order. Now I know what you're thinking. The order is a sequential task, right? And you're correct. The order has 2 steps: take the order and prepare the order. These are sequential tasks. However, if you have another order, which is again take the order and prepare the order, if you have another order, you can prepare these 2 orders parallelly. You can prepare order 1 and order 2 parallelly, like we saw in our restaurant example before, right? Both orders can go in parallel. So preparing a single order is a sequential task, which we looked into earlier. However, preparing multiple orders is a parallelizable task, because these orders are independent of one another, right? Now let's look at some real world examples. Here's a very good example of a parallelizable task, which is matrix multiplication. Now each cell in the matrix can be computed independently, right? They don't depend on one another at all. So if you look at this, the cell that's highlighted in red and the cell that's highlighted in yellow can both be computed independently by different threads at the same time, and they can give us the results at the same time. This is a very good example of parallelizable parallelizable task. Next, we have Fibonacci calculation. Now you might be confused, as in like we just discussed, Fibonacci calculation was a serializable task. But just like the order, an order was a serializable, sequential task. An order was a sequential task. However, multiple orders were parallel tasks, right? Same thing with Fibonacci. Calculating a single Fibonacci number is a sequential task, as we already know from the previous slides, right? However, calculating multiple Fibonacci numbers is a parallelizable task. Each thread can work on these tasks. Fibonacci of 5 can be calculated by one thread, Fibonacci of 8 can be calculated by another thread, and they can both give us the results at the same time, right? So this is quite similar to the single order and multiple order example that we discussed earlier. Next example would be web scraping. This is a very famous parallelizable task. We have 4 web pages here, and each of these circles represents a crawler which can extract data from the web page, and we can scrape these at the same time, and then we can extract the results, right? The final example that I want to look at is image rendering, where each pixel can be individually rendered parallelly, right? You can individually render each pixel like so. This is an example of a parallelizable task as well. So now that we've looked into the inherently sequential and parallelizable tasks, let us move into the next topic, which is advantages of concurrency. Now we've understood a lot about concurrency already, as in a general overview of what concurrency is and how it executes. Let's look at the advantages, right? So there are direct and indirect advantages. Let's look at the direct advantages first. The direct advantages are, we get improvement in code execution speed, as we saw already, right? With 4 chefs, 5 customers, the improvement in execution speed was there. Also, one more thing that was there was none of the orders had to wait, right? So non-blocking code execution is another direct advantage of concurrency. You don't have to wait for one task to finish for the other to execute. Now bear in mind that this is only applicable for parallelizable tasks. Sequential tasks do not share this advantage because they cannot be made concurrent, right? So next we have the indirect advantages, which is basically scalability. So we distribute the tasks upon multiple nodes. It should be cores, but yeah, whatever. So this allows us to execute a lot of tasks simultaneously and improve the code. And this allows us to scale the system. We can handle multiple tasks at the same time, right? So it is scalability. Next, we have fault tolerance. So if one of the cores falls down, as in our restaurant example, if one of the chef goes away and there are only 3 chefs remaining, they can still perform concurrently, right? So this is an example of fault tolerance, where your system can function even if one of the nodes go down. We have better resource utilization because we are utilizing all the cores properly. We have code modularity. Now this is a very indirect advantage, because if you're doing concurrent programming, chances are that you will organize your code into much cleaner structures, better functions, smaller units, right? Because there's only a specific part that you will make concurrent, so you will organize it better. So this is actually a programming practice that you will end up doing when you're doing concurrent programming. You have an overall better performance of code because of all the above mentioned reasons. So these are the indirect advantages. And now let's look into the disadvantages of concurrency. Like everything, there's always a trade-off. If there is something good, there's also something that it lacks behind in, right? So let's look at the direct disadvantages of concurrency. Like I said, there are synchronization issues. So there you'd have to coordinate the access of various processes and threads to different shared resources. For example, in the sequential task we looked at writing to a file in order, right? There were 4 threads, but still they had to write in order. So we had to synchronize the threads in such a way that the order is maintained. These kinds of synchronization issues arise in concurrent programming a lot. There will be not just writing into threads in order, there will be a lot of operations that need to happen in order. For those, we need to have synchronization issues, because if we don't, it will lead to race conditions. Basically, race conditions, again, we will discuss this in proper detail in the next upcoming videos. However, for now, what you need to understand is multiple threads may do some incorrect reads and writes into the files or some shared resource that we have, which may lead to inconsistent results. You want to update a value by 1. Let's say 2 processes want to update the value in a file by 1. The current value is suppose 7. Let's say thread 1 reads the value first, reads it as 7, increments it to 8, but does not update it yet. In the same time, thread 2 comes and reads the value, it's still 7, right? Because thread 1 has not updated it yet. And what that does is basically thread 2 will also read 7, it will increment it by 1 and turn it to 8. Now when thread 1 writes, updates the value as 8, and when thread 2 writes, it also updates the value as 8, which is incorrect, right? We had 2 threads which wanted to increment the value twice. However, because of race conditions, as in an inconsistent read condition, the value was only updated once. So this is a very small example of race condition. We'll look into it in much greater detail later. Then we also have deadlocks. This is when 2 or more processes are blocked by waiting for each other's resources. Say process 1 wants something from process 2, but process 2 will only give it if it gets something from process 1. So both of them are kind of blocked on each other, right? We'll also look into this concept in better detail later. So these are the direct disadvantages of concurrency. The indirect disadvantages of concurrency are as follows. Increased code complexity. When you write concurrent programs, your concurrent complexity increases dramatically. Like, you'd have to manage a lot of threads, a lot of processes. At the same time, you'd also have to write code in a way where you'd have to cater for different execution units, right? So overall, it increases the complexity of code. Next is, it is very difficult to debug. You never know which thread went down why. You do know, but it's very difficult to debug because sometimes the same process is being executed by 2 different threads. And if you want to debug, you see that one of the thread is working fine, the other is not. And it just means that there's nothing wrong with your code, the thread failed for some other reason. Now you might be thinking that would be a rare case, right? But no, the thread fails every time. The second thread fails every time. What do you do in such a case? You have to debug some memory issues. You have to debug a lot of other things. So it is very difficult to debug concurrent code. Next is overheads. Like we discussed, overheads, context switching, there's also other overheads like thread creation, thread deletion, and synchronization, right? These are all the overheads that you need to cater for when you're writing concurrent code. Then also, like we discussed earlier, it is very difficult to predict the order in which the threads will execute. That is why we need synchronization mechanisms in the first place, because the order is not guaranteed when you're executing code concurrently. The next is, it is very difficult to test. Even if you write unit tests, it is very difficult to test concurrent code in real time, right? By real time, I mean when it is executing. So these are all the direct and indirect disadvantages of concurrency. Alright then, great, we have made it so far. Thank you for coming here. And in this video, let's look at what we covered. We covered sequential versus parallel versus concurrent execution, understood the different terminologies, the different key differences between them, and how they execute in general. We looked at inherently sequential versus parallelizable tasks. We looked at the various advantages of concurrency and the disadvantages of concurrency, right? Cool. So in the next coming sections, we will look at every advantage of concurrency with practical example of code, right? We'll write code and look at the example of concurrency advantages, and we'll also write code and look at the concurrency different disadvantages of concurrency. These advantages and disadvantages would be direct disadvantage and advantage, because we cannot really write code to simulate indirect advantages. Those just happen. We can show the direct disadvantages and advantages using activity monitor and other tools. We will do that as well, and this is what we'll look into in the next sections. So that's it for this video. See you guys in the next video. Bye.